In the last lesson, we took a look at reciprocal functions of, well, linear functions or linear relations. And I think it makes sense to now take a look at the reciprocals of quadratic functions, which would be the next step up, given that in grade 9 you learned linear relations and in grade 10 you learned quadratics. So we're just going to do the exact same things, but 1 over. We'll start off with the most basic one, of course, which is 1 over x squared. And sometimes one of the easiest ways to do reciprocal functions to graph them is rather than do point by point, plug in x equals 0, 1, 2, 3, etc., although that will work. Sometimes it's nice to actually just graph what the bottom function is. So I'm going to start that here, and I'm going to use a fairly light color just so that you can kind of make it out. And let's do just the graph of f at x equals x squared, which is pretty simple. It's just a quadratic, specifically the graph of a parabola. And it looks something like this. And now what I want you to remember is that an inverse is just 1 over that. So if you think about point by point, what is 1 over everything? 1 over 0 right there. 1 over 0 is going to be an asymptote. So we'll have an asymptote there. And this is a general rule with reciprocal functions. Anytime the bottom is 0, the whole thing's going to have an asymptote, a vertical asymptote. Here we have 1 over 1, so it stays at 1. Our 1 over 4 up here becomes, our 4 becomes 1 over 4, or a quarter. And likewise, if we plug in x equals 1 quarter, we get out 4. And so we end up getting something that looks a lot like 1 over x. It's not exactly the same. It's a little bit different in how sharp it is, but it's about the same looking. What does change is that our negative x values are actually going to give positive reciprocals as well because they're getting squared. So instead of having this part over here in the third quadrant, like we did with 1 over x, we're going to have it mirror imaged in the y-axis, y-axis. Which makes sense. The parabola was symmetric, so 1 over the parabola, or 1 over the quadratic, I should say, since parabola is a shape and quadratic is the type of function that gives it. But 1 over the quadratic, if the quadratic gives a parabola that's symmetric, 1 over it should also be symmetric. And so that's what it looks like. The domain, x is going to be element of real such that x cannot equal 0. The range, y is the element of real such that y is not equal to 0. Oh, okay, so this looks like I just jumped to the completed question because I did. I realize there's a slight error, and I'm going to edit this part in so you can see what I did wrong. It was for the range, and I said that y was not equal to 0, but that is not true. Y actually can't equal anything below 0 either. The entire graph is positive or greater than 0. So that means it should be y greater than 0, not y can't equal 0. So there's the restriction on y. Now, unfortunately, when I edit this back in and continue, it's going to look like it says y is not equal to 0 again. Just ignore that and move on with your lives. And I can put the horizontal asymptote on there as well. The asymptotes, the vertical one is x equals 0. The horizontal one will be y equals 0. And the end behavior, as x goes to negative infinity and as x goes to infinity, well, y will approach 0, and it will be 0 on the positive side because it's coming in a little bit above 0, very close to 0, but still above 0. And that's actually the same for both of them. So as we go to both extremes, our values for f at x are getting smaller and smaller and smaller, closer and closer to 0. but will never actually reach 0 and will always be positive. And I just realized I'm going to change a value here. I'll change it on the PDF before I release it, but I'll change it here now. I'm going to change this to 1 over x squared minus 4. It'll just help us make out a little bit nicer on this graph. Okay, so I'm just going to point out that that bottom can be factored nicely. And that's 1 over x minus 2, x plus 2. So what that means is that I'm going to actually have zeros on the bottom at plus and minus 2, which means I should have asymptotes at plus and minus 2. I said I changed it to make it easier. We could have done it with x squared minus 2 on the bottom, but then we'd have these asymptotes at plus and minus root 2, which is just not as pretty. Okay, so now we have 2 vertical asymptotes. We're still going to have 1 horizontal at 0, because as x gets really big, whether it's positive or negative, we get 1 over a huge number minus 4, which is essentially 0. What happens in the middle? That's another story. Okay, so now I can try plugging in a couple various values for x and seeing what I get out on the bottom. If I plug in x equals 0, I get 1 over negative 4, which is negative a quarter. If I plug in 1 or negative 1, I get 1 over 1 minus 4 is 1 over negative 3, or negative a third. And as I plug in values closer and closer to 2, whether that's positive 2 or negative 2, I'm going to get 1 over almost 4 minus 4, which is going to give a small negative number. 1 over a very small negative number will give me a big negative number, which means that my graph's going to go down this way. Now I'll skip the plus and minus 2 for a second, because obviously those are going to give undefined answers. The asymptotes are there. But if I plug in plus or minus 3, I'll get 1 over 3 squared minus 4, 1 over 9 minus 4, it's 1 over 5. So I'll get small positive values there and there. And then as those get bigger and bigger, it'll just get closer and closer to 0. So I'm going to approach the asymptote as I move away. But as I move closer to the 2, either like 2.01 or negative 2.01, I'm going to get 1 over a number just bigger than 4 minus 4, which is 1 over an itty-bitty positive number, which is positive infinity. And because of that, I'm going to get an approach of the asymptotes that way. And I'm going to point out something in just a sec here, as soon as I've done drawing this. And that's that for these kinds of sketches, other than maybe a test value or two, I'm not too worried about getting exact values in these areas. All I really care about is that I'm kind of going through one point and that the others are approaching asymptotes. I'm not going to check. So I don't know if it's accurate right there or there, but it's close enough. We were accurate at this point, give or take. That's accurate enough for us. And that's the same with areas like here and here. Are those completely accurate? I don't know. I'm not too worried about it. What we're really looking for is what kind of shape or form it takes. And it turns out that that's what 1 over x squared minus 4 looks like. So now we'll just quickly go back and talk about domain and range. And for domain, I can say x is the element of real such that x is not equal to plus or minus 2. For the range, y is the element of real such that y is not 0, because there is no x value I could possibly plug in that would give me y equals 0. The asymptotes, there are two vertical ones we just saw, and that's x equals plus or minus 2. And if they were different numbers, we would just write them as, one comma the other. That's fine. Horizontal, y equals 0. And then the end behavior, this time it's a little bit weird. We can talk about quadrants, but that's not really accurate since in quadrant 3 it is approaching 0 and negative infinity depending on whether you're looking at the graph here or here. Although I will tell you right now that this part here is not technically end behavior because x is not going towards negative infinity, it's going towards negative 2. So our real end behavior is the other one, and that's as x approaches negative infinity, y approaches 0 from the positive side. And as x approaches positive infinity, y will also approach 0 from the positive side. And that's right over here. What it does in the middle is irrelevant. The middle has nothing to do with end behavior, only the extremes. Okay, so that was a little bit different looking than the other ones that we were doing yesterday or the last lesson with the linear functions on the bottom. Well, let's put another quadratic in and see what happens. Now I realize my choice of 1 over x squared plus 0.25 might seem a little odd, but bear with me. I will explain well, you'll see for yourself actually in a moment why it happens. But what I'm going to do is actually just graph x squared plus 0.25 and see what it looks like as a parabola. And again, I'm going to do it using a lighter color so that it doesn't take away from the extreme. So I'm basically just drawing a parabola and shifting it up a quarter. So this will be 1 1/4, 4 1/4. Same thing for the negatives. So I get a parabola that looks a little like this. Now if I want to do 1 over that, I just do 1 over each of the individual points. The easiest point to do is actually the x equals 0 value. Since the parabola is at 1/4, its inverse, 1 over 1/4, is going to be at 4. At 1 and negative 1, we're at 1 1/4. 1 over 5/4 is 4/5, so we're actually just a little bit below 1, but not by much. And then as we get towards bigger and bigger numbers, we can kind of almost ignore the quarter, the extra quarter. So the inverse of 4 1/4 is about 1/4. And sure enough, we get a graph that looks like this. Now this one's a little bit different than all the other reciprocal functions we've looked at so far. And the reason is there is no vertical asymptote. But that actually kind of makes sense since the bottom of this is never going to equal 0. Because we've got a squared number plus 1/4, the bottom is always going to be positive, no matter what we plug in for x. So that gives us a domain of x is the element of real. There is no x value that breaks that function. The range, well, we still do have a horizontal asymptote down there. So the range is y is the element of real such that y is not, yes, y is, oh, sorry. I'm going to say y is not equal to 0, but if I look closer, there is no y anywhere down here. Or no graph, I should say, no function. So that means that y is actually strictly greater than 0. So it's not just not equal to 0, it's not equal to 0 or anything negative. Our asymptotes, vertical, there is none. Normally I wouldn't bother writing that. I'm just going to remind you that there is none in this case. It's not that we forgot. Horizontal, y is 0. For the end behavior, as x approaches negative infinity, y approaches 0 from the positive. And as x approaches infinity, y approaches 0 from the positive as well. Okay, so just really quickly to look back at the last two, I think you'll see that there's a drastically different appearance in the graph if we look at what happens when the quadratic on the bottom is x squared minus a number and what happens when it's x squared plus a number. It's dramatically different because the bottom in this case cannot equal 0, so there will be no vertical asymptotes. So it's quite a bit different. Okay, what about something like f at x equals negative 1 over x squared plus 3x minus 4? That's a relatively complex, well, I mean, it's not super complex, but it's a quadratic with about everything going on that could be going on. We have a negative sign in front. We have 3 terms. I'm going to tell you right now, the easiest way pretty much to figure these out, or at least to start graphing, is to factor them. If we see them in factored form, they tend to be easier to deal with. So the negative 1 over part, that won't change. For the x squared plus 3x minus 4, we're looking for two numbers that multiply to negative 4, add to positive 3, and I think those numbers are going to be plus 4 and minus 1. And when I say I think that, I'm pretty sure. Okay, so what that means is we're going to have two asymptotes, just like we did in our earlier example, except they're not going to be symmetric. One of them will be at negative 4, and one of them will be at positive 1. So now we have to figure out what the rest of the graph is going to look like in between. So let's try plugging in a few numbers. And when you're plugging in numbers, it doesn't matter whether you're looking at the original equation or the factored form. When I plug in numbers like 0, I'm going to get negative 1 over negative 4 is positive a quarter. When I plug in negative 1, that's going to give me, on the bottom of the fraction, 1 minus 3 minus 4 is negative 6. Negative 1 over negative 6 is 6. Okay, so that's actually going to be up here off the graph. Wait a second, did I do that right? Oh, wait a second, I said it's going to be negative 6 on the bottom, so that means that it's 1 over 6, not 6. So pretty close to the axis down here. And then at negative 2, I'm going to get 8 minus 6 minus 4 is negative. I think when all is said and done, I'm actually going to get 1/6 again. Okay, this might actually work out okay. And when I plug in negative 3 on the bottom, I'm going to get 9 minus 9 minus 4 is negative 4. Negative 1 over negative 4 is 1/4. Yeah, we're getting some symmetry now between those two asymptotes. And I think what you'll see is that if you choose a number that is very close to 1 but a little bit smaller than 1, you're going to get a number smaller than 1 plus a number just smaller than 3 minus 4, which is going to be a very small negative number. Negative 1 over that's going to be a very big positive number. And so again, I'm just trying to sketch the quality or what this graph is going to kind of appear like. I'm not worried about getting the exact values all the way along there. And it's going to be very hard to get them anyway because they're extremely finicky. Now, what if I plug in 2 on the bottom? 2 on the bottom will give me 2 squared is 4 plus 6 minus 4 is negative 1/6. So about there. And because of symmetry, I'm pretty sure it's going to do the same thing here. And I think I can justify without too much problem. Sorry, that's a really bad asymptote, but I think you can see that it's along the x equals 0 or y equals 0. We're going to get a graph that looks like this. Which actually makes sense. This looks fairly similar to the first one that we did, or I shouldn't say the first one. Let me just scroll up for a sec. Looks a lot like this one, but upside down and shifted over a little bit, which makes sense because it should be upside down. And because of the asymmetric values that we've got for our asymptotes, it is shifted over a bit. Okay. So basically, the graphs that we do like this are going to fall into the two categories when we're doing the inverse of a quadratic. It's either going to be places where the bottom can be 0, in which case it could have 1 or 2 roots, or 1 or 2 zeros, which means 1 or 2 asymptotes. Or the bottom could be so that we can never get a 0, and then we have no vertical asymptote at all, so something like that one. Oops, I don't want that. Okay, so let's really quickly fill in this table here. I think we're probably at this point beaten all these domain range asymptote stuff to death, but it should be getting pretty quick. Domain x is the element of real such that x is not equal to -4 or 1. The range, y is the element of real such that y is not equal to 0. It looks like y can be any value bigger than 0 or smaller than 0, since we have some graph on the top and some on the bottom. And our asymptotes, we got the vertical, x equals 4 and -1. Sorry, -4 and +1. Horizontally, y equals 0. End behavior, as x goes to -infinity, y goes to 0, and you can see at the ends that it's actually going to be just below the axis. So that means it's going to go towards 0, negative. And as x goes to +infinity, y is going to go to 0, negative as well over here. And let's do a rate of change just because we can. So we're going to do it on f at x equals 1 over x squared minus 1 at x equals 3. Just to remind ourselves that rate of change is really easy to find. It's basically find the slope, and right now we can use that, the secant method to do that, which means look at this change of y over a change of x for a very, very small value near the desired point. So we'll say m is going to equal f at 3 and a little wee bit. So I'll say 3.01 minus f at 3 over 3.01 minus 3. Okay, so 3.01 squared minus 1 is 8.0601, and then 1 over that is 0.12407, or something like that. When I plug in x equals 3, I get 1 over 9 minus 1 is 1/8, which is 0.125 exactly. And on the bottom, I get 0.01. So now when I plug that in, I get the 0.12407 minus 0.125 is negative a little wee bit times, divide by 0.01. And I'm still getting a very, very, very small value. Negative 0.0093. So it's a negative slope, but it's a very small negative slope. Why don't we go over to Desmos and just make sure that that makes sense? Okay. So we want our function to equal 1 over x squared minus 1. So that looks kind of like the ones we were graphing. And we want to know its slope at x equals 3. So at 3, 0.125. Okay, oops, I don't know why that's a subscript. And what we're looking at right there is, can we find a slope that makes the green line match the blue? And yeah, we can see that it's going to be negative. It's actually pretty close to negative 0.1. Let's see if we can be more precise. I'm not sure that we can. Okay, we're zoomed in a lot there, and I still don't see much of a difference. And that makes me suspicious about the value I got on my other sheet. So let's go back and just double check that. Okay, the good news is I'm just double checking my calculator, and I think I just goofed on the decimal placement there. So I don't think it's 0.0093. I think it's just 0.093. Oops. And our graph told us it was approximately negative 0.1. I'd say that's pretty close. So I think we've got that one nailed. Okay, I think I'm going to stop there, give some questions a shot, and the best of luck to you. Otherwise, we'll see you in the next lesson.